Next speaker is Pedro Salomão from the University of Sao Paulo, and he will be speaking about a dynamical characterization of length spaces.
Okay. So, thank you very much for the invitation. And so this is a joint work with Humberto Irinievich from Federal do Rio de Janeiro and João Licata, Australian National University. And the question that I'll talk about is concerns about understanding the topology of a contact manifold. Suppose that you have a contact form defining that contact structure, and you look at the Hebb flow of this contact form, and you want to extract some information about the topology of the manifold and the topology of the contact structure. So I just learned this week that from Hutchings' lecture that he had an example of this type of question, which was the example that he said when you have a contact form with precisely two periodic orbits, then it must be a length space. And the question will be exactly on length space. We're going to look at some Hebb flow and see some information about the periodic orbits, and with some hypotheses, we will deduce that the contact structure and the contact manifold is the length space with the standard contact structure. Just to give an example, it's a not so recent theorem by Hofer, Vysotsky, and Zender. They give conditions to characterize the type 3 sphere, which is the following. Suppose that you have a contact manifold and you put a contact form and you look at the Hebb flow and you find a periodic orbit which has these three properties there. Well, first, let's assume that the contact form is non-degenerate. So the Hebb flow, all the periodic orbits are non-degenerate. And it's dynamically convex, which means that so you have well-defined Conley-Zender index for all the periodic orbits. For instance, assume that the contact structure is trivial, and suppose that the Conley-Zender indices are all at least 3. And now assume that you have this periodic orbit, which is unknotted. So it spans an embedded disk, and it's self-linking number. So the first condition is topological. The second condition involves the contact structure. We assume that the self-linking number is -1. And the third condition is dynamical, which we assume that the Conley-Zender index of these orbits is exactly 3. So in this situation, then you prove that the contact manifold that you have must be the type 3 sphere. So the standard 3 sphere with standard contact structure. I'll talk about that later. And this is a characterization theorem because the converse is always possible. It's very easy to prove. The difficult part is to prove that the manifold must be the type 3 sphere. So with those conditions. And the proof involves producing an open book with exactly that binding orbit. And this open book is formed, all the pages are disks with the boundary in that periodic orbit. And these disks are all transverse to the Rip vector field, and then all this information gives you the topological information about the contact manifold. It must be the S3 with the standard contact structure. Okay, just to give some definitions we consider M, a three-manifold, closed and connected, and the lambda contact form, which is lambda wedge, the lambda is non-zero. And its Rev vector field and the contact structure is defined by those equations. The Rev vector field is in the kernel of d lambda, and it's normalized by being equal to 1 with lambda. And the example, which is the toy model, is to see that the Liouville form in R4 restricts to S3 as a contact form. And related to this contact form on S3, we can multiply by a smooth function, positive smooth function, and you obtain a new contact form. And the real vector field of all these other contact forms, they parameterize the Hamiltonian vector field on a regular star-shaped energy level in R4. And also, you can lift the geodesic flow on S2 to this type of contact form, and study the geodesic flow on a star-shaped energy level, which is symmetric with this type of form. And, okay. So the type 3 sphere, which is a very good example to talk a little bit about that. So when we restrict, we can see S3 inside C2, and all the orbits are periodic, the same period. And we have this, let's say, special periodic orbits, and here in this second factor, it's 0, and here it's the unit circle, and let's call this periodic orbit inside S3 by L1, and there is another one, which is just the opposite. And so all the other periodic are periodic, but all the possible combinations of radius inside S3. And so let me just define that this is the kernel of the Liouville vector field restricted to S3 is the standard contact structure, which is tight. It's a topological property of contact structures. And these two Hopf fibers that I just mentioned, they have this nice topological properties. They are embedded. In fact, we can construct an embedded disk for each one of them. Let me just draw the disk for L1, which is just the product of this disk and this interval here inside S3, which is an embedded disk. And this other periodic orbit, and this point corresponds to the center of this disk, is linked in this way. And so each one of them, there is another embedded disk to this other orbit. This one is embedded, and there is this contact invariant called self-linking number, which is -1. I'll not define that. So how do we define lens spaces? We take an action on S3, which is the following, is just a ZP action, and take two positive integer numbers, which are relatively prime, and then you take the action generated by, in the first factor, you rotate by 1 over p, and the second one you rotate by q over p. And you take the quotient of S3 under this action here, So you have this lens space LPQ. And since the contact form, the Liouville contact form is invariant under this action, so it descends to a contact form on the lens space, and also, of course, the contact structure descends to a contact structure on lens space. And so you have what is called the standard contact structure on lens space, the same, denoted by the same way. So the question is, what happens with this picture when we go to the lens space? So this orbit here will there will be P points which will be identified. So this orbit projects. So here, let's say it's S3, and here LPQ, and this one descends to a closed orbit for the standard contact form on the lens space. But that disk is a little bit different because the interior of this disk will not be multi-covered. It projects as an embedded disk downstairs. So it's a little bit more difficult to draw here, but there is an embedded disk inside LPQ. But the boundary of this disk covers P times now the projection of this knot downstairs. So it's just like that. Let me draw this picture just to try to explain a little bit more about this. So the knot downstairs will be here, and that disk will be something like that. There will be many branches of this disk approaching each point of the boundary. Okay, so where is Q, the number Q? P we see here as this number of branches and how this knot descends, P covering it, and how we see this other integer Q. We can see this way. We can follow one of those branches along the knot, and when we are back to the same point, it rotates by. It's not the immediate branch that we see here, but it's some branch that is rotated by Q. That's how we see this other integer number. We just move it to another branch which is rotated by Q. So our P disk is like that. So that's what we call a P disk, and so downstairs this knot here is called a P unknotted because it admits this embedded P disk which P covers it in the boundary, but in the interior it keeps being embedding. Now we could do the same thing to this other guy here, and also the projection will cover P times, but now this number Q is not exactly Q, it's the inverse of Q mod P. It's always this inverse. So this number Q in this example is what we call the monodromy of the knot. So in this example, the monodromy is Q. So we have this P knot with a monodromy Q. So there is some orientations, which is, that's why that sign is minus. But the picture is that. the theorem is the following. So we want to do the same, that something very similar to that theorem of Hofer, Vysotsky, and Zender. And we assume the existence of this P and not. And we want to prove that under some assumptions, our contact manifold must be exactly the length space, LPQ, with the standard contact structure. So we assume the existence of just one periodic orbit and some other properties that I will say. We can relax the condition of the contact form being dynamically convex, could have orbits with index 2. So the theorem is the following. I will just say one of the directions of this characterization, which is the following. Suppose that you have a P and not, just like this one, in length space, which has this monodromy equal to Q. And we want to find conditions which imply that the contact the contact structure is the standard contact structure on the manifold, and the manifold being the length space. So we assume that we have a contact form defining that contact structure, and we look at the Hebb flow of this contact form, and we assume that this knot here is tangent to the Hebb vector field, and the index of the P iterate of this knot is at least 3, and the self-linking number is minus P, and the monodromy is exactly Q. We have another condition to help us in the compactness argument, which is to avoid the orbits with the index 2. They are kind of a problem here in the analysis. For simplicity, I just put that we assume that the contact form is not degenerate, and if it has a periodic orbit with the index exactly 2, then it must be not linked to the given knot, which means that the intersection number of this other periodic orbit is 0 with this P disk. So these are the assumptions, and the conclusion is that in this case, if you have a Hebb flow with this hypothesis defining that contact structure, then the manifold must be the length space and the contact structure must be the standard one. Let me draw the very simple, which is the following. I will like slice the P, this P knot, and I will draw the P disk to it, something like that. Just we are assuming its existence. We have the contact form, and this is a closed Hebb orbit, and this is the P disk. It might be very any P disk, and the strategy of proof is the following: is to produce a P disk to the same knot here, but now it's pseudolomorphic. It has very good properties. And out of this P disk with very good, nice properties, like asymptotic properties, to this given knot, it's P covering it, then you can produce nearby P disks by applying Fredholm theory with the suitable waves and foliate all your manifold with such disks. Of course, to foliate the rest of the manifold, you need some compactness, and the compactness is given by that assumption on the index 2 orbits. And so you have a compact family of such disks, foliate as a S1 family, and all of such disks will be transverse to the Hebb vector field, And in the end, if you have produced this open book decomposition for your contact manifold, this will imply that the manifold is a lens space and the contact structure is standard. So this is the strategy.
It's a rational number.
Exactly. So yeah, the boundary P covers the given knot. Exactly. Just a very quick review on the theory of pseudo-Lamar curves in symplectizations of three manifolds. We have our given contact form lambda, and we can consider the symplectization by just multiplying our contact manifold by R. And the contact structure is a symplectic vector bundle over the three manifold. You always have these complex structures, which is the lambda compactible. And we can choose one of such J's and produce an almost complex structure in the symplectization by saying that the R direction is sending the read vector field and the contact structure is preserved by coincides with that given J. And so we take this curve satisfying that equation, and it's defined on a Riemann surface, and possibly we remove a finitely many points from this Riemann surface. If this surface has a boundary, we remove only interior points, and we assume that the energy, Hofer's energy of this curve is finite, and you have good asymptotic limits at all of those punctures. Let's assume that all of them are non-removable. So the first part of the proof is just to show that you have the given P disk, which must be very complicated, and we would like to produce a pseudolomorph P disk. So the given P disk, I will draw this way. And we can slightly perturb it. It's a very well-known trick. So that the characteristic foliation is the following. It has only one singularity point, and all the leaves issuing from this singularity will hit the boundary transversally. So here we assume that here we use that the contact structure is tight, and also that the self-linking number of this P not is equal to minus P, just to produce this characteristic foliation. And we need a few other assumptions on this P disk, which is we can perturb it in a C0 way, so that it's still an embedded disk in the interior. And we need some more, which is the following. In a very thin strip near the boundary, here, of this perturbation, it must be transverse to the read vector field. Excellent. Must be transverse. And the reason for that, we can always do that, because the index of the P iterate of that knot is at least 3. It's always possible to perturb here, such that the read vector field is transverse. And we also assume that this disk here, this point is where the contact structure is tangent, that this disk does not contain any periodic orbit of the Hebb flow. The only periodic orbit is in the boundary. nothing inside here. And now the most important thing also, with another small perturbation, is the following. We take Darboux coordinates near that point, which takes the contact form in this way. And the origin corresponds to this singularity E, which is elliptic. And this disk, at least very nearby this point, corresponds to that surface, minus 1/2 xy, which here you're going to see something like a saddle. Just like a saddle. You would see something like that. It's a very... So when you do that, then you can choose J in the contact structure very appropriately, which is the kernel. The contact structure in this way is spanned by del x and del y minus x del z, these two vectors. And so you can just define locally near this point J is, let's say, E1, E2, and J E1 is equal to E2. Then, what is good about all these choices is that you can solve the pseudo-holomorphic equation for disks. And you find very nearby pseudo-holomorphic disks emanating from the singularity. And there is an explicit formula for those disks. It's a family of solutions. It depends on a parameter tau here. So very small disks converging when tau goes to 0 to the singularity and emanating from it and winding the singularity exactly once. And so we have a starting point to produce this, the P disk, which is pseudo-holomorphic. So we can check about the compactness of this family of disks. Locally, it's a one-parameter family after parametrization, after quotienting with the parametrization. And we can look what happens with these disks. So the boundary, here is the singularity, here is the R direction, and these disks are like that. Our P disk, the new P disk after perturbation is here, and we can see what happens when you try to go to the boundary of the given P disk. So it must bubble. It cannot be a compact family, otherwise it would reach the boundary, but the boundary is a periodic orbit, and by degree theory argument, so we cannot touch it. There is some obstruction. This family of disks cannot touch the boundary, so it must bubble. And if you choose a very good parametrization of such disks, then the bubble is far away from the boundary. We don't have to worry about bubbling points in the boundary. They are all interior points after choosing a good parametrization. So you produce a bubbling tree out of this break, and this bubbling tree starts like could have many different levels and so on, let's say here, but at some point must finish, and you have at the bottom of these three planes. And so here it's where you need that assumption that I said about index 2 orbits. So if it bubbles like that here, before reaching the boundary, it will produce a bubbling tree exactly like that. And so it's possible to analyze what is happening with these periodic orbits that are asymptotic of each curve in this bubbling tree. And there is a topological argument which says something like that. If the index, let's say in this level, is 1, which, well, these orbits coincide, then it's also 1, then at least one of these negative punctures of this curve must have also a periodic orbit with index at most 1. So you can keep doing that until you reach the bottom of the tree, and you're going to conclude that there is some plane which is asymptotic to a periodic orbit with exactly index 1. That's impossible for topological reasons. So all these asymptotic limits here have index at least 2, cannot be low. So there is another argument to say that now if you start from the bottom and you assume that the index here is 3 or more, then you're going to go up this argument and to produce here an orbit with index 3 or more. And this is not possible for this, in the top of the tree, you have some Maslov index of this curve. And for generic J, this punctured disk cannot have index 3 as a negative puncture. So we can exclude this situation. Cannot have any index greater than 3 in this bubbling tree. So we conclude that all orbits in this bubbling tree have exactly Conley-Zender index 2. So you have this type of break, you in the end produce downstairs a plane asymptotic to an index 2 orbit. And this plane, because of intersection arguments, will not intersect the given P disk. So it's not linked. But if you assume that such orbits with index 2 do not exist, then something is wrong here. Cannot break this way like that. So this family must continue until it reaches the end of that P disk. But when it reaches the end of that P disk, it must break in the same way. But now the bubbling of 3 is something like that. This is the given periodic orbit, and arguing is in exactly the same way, you produce a plane to the given periodic orbit. That's the only possibility. And this plane has some nice asymptotic properties, which is seen in an invariant called Y infinity, which is well defined also because we assume that the contact structure, it's C1 vanishes on pi 2. So all these numbers are well defined, and with this good asymptotic properties of this plane that we have produced, well, it does not intersect the boundary, and the projection on the manifold is embedded. So we obtained in the end our P disk, which is the projection of a pseudomorph curve, and then we can apply Fred-Hund theorem and make a second round of compactness to show that this lives in an S1 family of such disks. And finally, we obtain that the manifold must be LPQ, and the contact structure is standard. So another application of this method is the following. All this theory can be used not only to produce characterization theorems, but also to produce global surface of section. And when we have these assumptions, now let's assume that we are already in the LPQ and with the standard contact structure, and you have a one form with that given periodic orbit, which is P and naught, and monodromy Q. Then with those assumptions, you can produce an open book. So, and each page of this open book is a global surface of section, which means that all the orbits will hit that given P disk infinitely many times in time. And so we have also this type of theorem to produce global surface of section. And the theorem is exactly that, the same one, but now we assume that the contact manifold is LPQ with the standard contact structure, and you have this P and naught with the Conley-Zender index at least 3, and all the orbits with the index exactly 2 are not linked to the given one. Self-linking number is minus P, and you produce this open book in the same way. And there are these three equivalent situations. Whenever you have one of those pages, you produce the open book, and each page of the open book is a global surface of section. And so all come together. Okay. So let me just give 2 examples to where we could apply this theorem, which is the following. This geodesic flows on S2, and possibly in the planar circular restricted three-body problem. Both of them, we have a Hebb flow on a lens space, which is just L2-1. And both of them, you have the standard contact structure. So all these theorems apply for these types of flow. The first application is very simple. There are 2 applications for geodesic flows. Let's assume that we have a surface of revolution around some axis, and you have the meridians here, which are closed geodesics. So when you take the double cover of these meridians, you have exactly one. For P equal to 2, it's 2 and naught. The self-linking number is minus 2 with our conventions. And its index is 3 or 4. So we are considering these meridians. So we are in the hypothesis of the theorem for producing global surface of section with just one binding orbit, just one boundary component covering twice. And all the orbits, since you have a first integral, and all the orbits will be linked to that one. In particular, all the orbits with index exactly 2 will be linked to this given one. Even if you have, for instance, here with negative curvature, you have index 0 orbit. You could have index 2, but this one with the index exactly 0. In fact, this implies that there exists an orbit with index 2, degenerate, but they are linked. So in this situation, you can find this global surface of section associated to each meridian. Of course, this is a limiting process because we put some assumption on the contact form that it's non-degenerate, and here it's very degenerate, but it's possible to push to this degenerate case all this global surface of section. And but of course here it's very easy because you have Birkhoff annulus. So you still have many other global surface of sections with annulus time. So it's nothing really new. Another example is for Finsler geodesic flows on S2, which possibly are not reversible. You have the reversibility of the Finsler metric, denoted by R. It's a number which is at least 1. Exactly 1 when it's reversible. The geodesic flow is reversible, but could be greater than 1. And with that pinching condition on the flag curvature, you have two things. By theorem of Harris-Paternai, you have dynamically convexity, and also by a theorem of Rademacher, you have a simple closed geodesic. So in the Finsler case, if you have a simple closed geodesic, you don't know if running in the opposite direction, you still have a geodesic. In general, it's not true. So when you have just one simple closed geodesic, you might have not the opposite orbit to try to construct a nonulus type global surface of section. But in this case, when you have just one simple closed, you can apply that theorem. Because with this pinching condition, you have dynamical convexity. So you have in its unit tangent bundle, which is L21, this open book decomposition associated to this knot here, given by this simple closed geodesic. And this open book, each leaf double covers this given closed geodesic. So we have an existence theory of a periodic orbit which fits the hypothesis of our theorem. So another application of is still a work in progress is the following. So you have the planar restricted tribody problem, circular restricted tribody problem. You have two bodies. One is much heavier than the other. They are moving in the plane, and you assume that they are moving a circular orbit. And you put some rotating system so that both bodies are fixed, let's say, in this X. And now you put the third body with no mass, and the movement of this third body is influenced by this. In this rotating system is influenced by these two bodies. We consider the ratio of the mass ratio very close to 0 or to 1, depends on how you see, so that the mass is concentrated mostly in one of these primaries. And so there are many recent results about Albers, Frauenfelder, Paternai, von Kort, Chili-Bach, Joel Fish, and Hofer that show that we can study this problem, let me say, for low energy, which means that this third body is trapped to move either around, let's say, the Earth and the Moon. This is the heavy body and the light one. So the third body will move around here for low energy. And Of course, there might be collisions here, but it's possible to regularize this problem to avoid, and so that you compactify the energy level, and after compactifying, you show that the Hamiltonian flow of this third party is in fact a Hebb flow on the length space L21 with the standard contact structure. So they have these results that there's so many statements. The first one, that you can study using all the tools from Hebb flows, and the second one that so near the moon, the light party, they show that such energy levels below the first critical level, which is, there is some point here, which is below, which is when you have these two components, the flow is dynamically convex if you take mass ratios, very small. So it's a dynamically convex Hebb flow for the standard contact structure on a length space. So you have a global surface of section. But when they show that they lift it to S3. So you have this global surface of section on the lift, not downstairs. You have to see if it's not clear if you can produce this open book decomposition on S3, you can push it downstairs. So this theorem in this situation would provide open book decomposition for instance, in the same situation where they prove it's dynamically convex, downstairs in RP3, directly in RP3. Well, the only problem, of course, is if you can really find a periodic orbit with those properties, which is, because when you take an orbit upstairs, which is the boundary of the open book decomposition, you don't know if it projects as a 2 or not on RP3. So you have to find those orbits here, and also here there are some results, because here you can approximate the third body movement by the Kepler. When mass ratios are small, you can use the Kepler, the rotating Kepler problem to approximate in this component. And in this case, they also show it's dynamically convex. But in this, now, they show it's dynamically convex, but they, in fact, to prove that, they do not show that the energy level is convex, because in some cases it's not anymore. They just compute the indices of all the orbits there, and they show that the indices are at least 3. So it's dynamically convex for the rotating Kepler problem, which approximates this component here. And, but in some cases, which are very close to this critical level, they show that it's not convex anymore. So when you perturb the rotating Kepler problem to obtain results for the 3-body problem, you don't know anymore if it is dynamically convex, but because you don't have the geometric convexity. So in this case, those results might apply in the following way. The rotating Kepler problem has 2 very special periodic orbits, which are the retrograde and direct orbit. So the retrograde has exactly index 3, but the direct one, the indexes could be much higher. In fact, the only one which has index 3 is the retrograde. Direct has higher index. And in this situation, and also the topology of these 2 orbits is exactly that one. These orbits form a Hopf link, and they both are 2 and not, self-linking -2, and you have dynamical convexity. And so when you perturb to the three-body problem, that situation, well, for many levels you still have convexity, but for levels close to the first critical level, you might not have any more. And in this case, orbits with index less than 3 might appear. But even if they appear, they would have very high action. And I did not mention that theorem, but I put as a condition that the orbits with index 2 might not exist, which are not linked to that given 2 knot. But you can do something, a more careful analysis to show that, well, we don't need so restrictive assumption. You could have orbits with index 2, but if the action is very high, also in the analysis, they will not be a trouble. You could also produce the open book decomposition if those orbits with index 2 are very high. So in this situation, this perturbation from the rotating Kepler problem to the three-body problem, we expect that when the direct orbit survives, you would still have an open book decomposition associated to the direct Webb orbit, which is another application for this three-body problem. Okay, but of course, it's still in progress. I'll stop here. Thank you.